Before we move on from polar to nonpolar molecules, I actually want to take a quick look back at what we talked about in the last lesson. And this molecule of water that seems to pass the mirror test, it does pass the mirror test. You can flip it, and you have the same thing on both sides. We said the reason that it failed is because of these lone pairs. And I just want to make sure that we're all clear on the fact that when you have lone pairs, you have a sort of pooling of electrons. That means oxygen's got 4 electrons, spend a lot of time around it. And electrons have a negative charge. So the fact of the matter is that when you have a central atom that has any number of electrons that spend more time around it than they do anywhere else, then what you have is a pooling of negative charge. That's why lone pairs around the central atom generate a polar molecule instead of a nonpolar molecule. It's that pooling of negative charge. Now, on to nonpolar molecules. We said that a polar molecule is asymmetrical, nonpolar molecule is symmetrical. Imagine a magnet with no poles. It's not a magnet. All right. So now we're looking at an equal sharing of electrons, which means that we have to have a bond, if we're talking about a nonpolar bond, between 2 atoms of the same element. So if it's just 2 atoms, they have to be 2 atoms of the same element in order for it to be a polar molecule. If it's more than 2 atoms, it gets more complicated. We look at the same 2 things. Does it pass the mirror test? If it does pass the mirror test, then it is nonpolar. That means it can be folded to reflect itself. And the second rule for identifying whether something is polar or nonpolar, same as before, are there lone pairs around the central atom? If there are no lone pairs around the central atom, then we would say the molecule is nonpolar. There is no pooling of electrons. We're going to start with the simplest kind of molecule, which is a binary compound like Cl2. And it's pretty easy to see that no matter what we do, Cl2, top to bottom, left to right, is symmetrical. You can flip it across any axis and you get the same thing. Since it's only 2 atoms, there is no central atom, we don't have to do the second test. So we say Cl2 passes the mirror test, which means it is a nonpolar molecule. And this is true for all diatoms. All of the diatomic elements. And remember, we said those are the 7-up elements. All diatomic elements are non-polar because they pass the mirror test. Our second example, CO2. First, we have 3 atoms. There's 2 oxygens and a carbon, and it's the carbon that will be the central atom because it has the most unpaired valence electrons. So if we look at carbon, it has 1, 2, 3, 4 valence electrons. And what ends up happening is that we have 2 bonds this way, 2 bonds this way. Just want to draw it so it looks as symmetrical as possible. All right, a total of 8 electrons around all the elements, 2 shared pairs to the left, 2 shared pairs to the right. Now when we look at this, CO2 is symmetrical. From left to right, if we have it this way, it's symmetrical top to bottom. It's doesn't matter what we do, CO2 can be flipped across any axis and you get the same thing. Now we look at the carbon. Are there any lone pairs around the central atom? No, there aren't. So our two tests, CO2 passes the mirror test, and there are no lone pairs around the central atom. So this is a nonpolar molecule. All right, again, you look at it, it passes the mirror test, and there are no lone pairs. Our final example is something we call carbon tetrachloride. Again, carbon is the only one here. It's the atom that has unpaired valence electrons. So we look at it as 1, 2, 3, 4. There's your chlorine, 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 chlorine. We finish out all of their valence shells. And we have our 4 dashed lines. So if we look at this, we would say carbon tetrachloride, no matter how we flip it, passes the mirror test. All right, so first up, it passes our first test. The second test, we're looking again at the central atom. Carbon forms 4 bonds, which means there are no lone pairs left. Each bond is a shared pair, meaning 8 valence electrons are accounted for, full valence shell. So carbon tetrachloride has no lone pairs around the central atom. And that means, this would be nonpolar, again. Now, one really important thing, distinction to make here, is the difference between a polar bond and a polar molecule, or a nonpolar bond and a nonpolar molecule. And in order to do that, I'm going to go back to the beginning. This bond is a covalent bond between atoms of the same element. That means that's not only a nonpolar molecule, it's also a nonpolar bond. So it is possible to have a nonpolar molecule with a nonpolar bond. It actually doesn't sound weird at all. It sounds very logical. Nonpolar bond, nonpolar molecule. But this, or these, I should say, are polar bonds. Despite the fact that we have 2 sets of polar bonds, the reason this ends up being a nonpolar molecule is because when we draw what we call the dipoles, oxygen has an electronegativity of 3.5. Carbon's like 2.6. So the electrons are pulled more in this direction than they are in this direction. Okay, there's a positive dipole and a negative dipole. Well, the same exact thing is happening on the other side. It's another oxygen with an electronegativity of 3.5. So I've got my positive dipole and my negative dipole. We have a tug of war going in exact opposite directions, and the electrons are being pulled by exactly the same element. So you have an equal and opposite tug of war going on, which means these dipoles, what we would say is the dipoles cancel. They cancel each other out. And that's why, even though you have polar bonds, you still have a nonpolar molecule. Really, really important to understand the difference. Polar bonding can still occur between or within a nonpolar molecule. The same thing here. We're looking at covalent bonds between carbon, it's about 2.6, and chlorine, which I believe now they're saying is 3.2. Well, those electronegativities are different. That means that you've got 4 different dipoles, one going this way, one going this way, but they're equal and opposite. You've got one going this way and one going this way, but they're equal and opposite, which means, again, we would say the dipoles cancel. And since electrons are being pulled unequally, but they're being pulled in sort of equal and opposite directions, in other words, the chlorines pull up and down with the same force or desire for electrons, they have the same electronegativity. And as we have it drawn, the chlorines pull to the left and right in equal and opposite directions. They cancel each other out. So these 4 polar bonds still result in a non-polar molecule.